Hello. Welcome to the second lecture in this romp through our discussion of what is artificial intelligence. In part two, we're going to consider what is artificial general intelligence. So let's consider our roadmap. First, we're going to think about some of the general background and historical context as it relates to human intelligence and the nature of the human mind. Then we're going to focus more specifically on computational functionalism as a theory of the nature of the mind, a very popular and widely influential theory of the mind. Then we're going to look at the Turing test and how this would allow us, hypothetically, at least one way to test for intelligence in an artificial machine. And then we're going to look at an argument for the possibility of some form of super intelligent artificial intelligence, some super intelligent computer that one day might possibly exist in the future. And then finally, we're going to look at some of the objections to that argument. But I suppose the first thing we need to do is we need to consider what exactly is artificial general intelligence. Now, there's probably no, unproblematic or non-circular definition that we could offer. At best, we can give a kind of what's sometimes referred to as an ostensive definition. And so if that's the kind of definition we might go with for what we mean by AGI, one way we can think of that is in terms of what Sam Altman, who's the creator of OpenAI, how he has defined what we mean by AGI. Altman says that AGI is understood or should be understood as essentially being equivalent to what he calls a median or normal human being. So, if we were to be rather blunt, then we could define AGI as being something that could be hired as your coworker, an artificial intelligent machine that could be hired to replace you, perhaps, replace your job. Another way to think about that is that AGI would have the ability to figure out or learn how to do anything that a median or normal human being could learn to do. Anything that you could do, it could do too, maybe even better. So, take for example a coder. If you can code, then an AGI can code, or it could at least figure out. It would have the ability to learn how to do that. I think this is a really interesting example because back in the day when I first started graduate school, this is around 2015, I started hearing people say the best degree you can get is like a degree in computer coding, right? Learn how to be a computer programmer because all of the future jobs are going to involve coding, and that was a very popular thing for people to say, and a lot of people went into that degree, that field. And interestingly, now we have AI that are doing the coding for us, right? So it turns out that being a coder is maybe not the best field one might want to go into. I'm sure it's still a very, very great field, lots of jobs in that area. But in the future, very likely we'll have artificial intelligence or some kind of AGI that will be doing the coding for us. Or consider a doctor or a nurse, right? If you can learn or figure out how to be a doctor or a nurse, then an AGI could also do that. Or a teacher, or a scientist, or a lawyer, maybe a politician, any kind of a job, any sort of field, anything, literally like a factory worker, anything at all, literally anything that you can do or that I could do. If we can learn how to do it, we can figure out how to do that thing, then an AGI can too. So that's the definition that Altman gives us. Now, when we're thinking about that, we might ask, how does this apply to a super intelligent AGI? Some kind of AGI that surpasses human intelligence. But before we get into that issue, let's kind of back up a little bit and think about how we can use this definition as being essentially equivalent to you or me, and how that applies to what we mean by the human mind in general. We need to begin with a man named Alan Turing. Alan Turing was born in 1912 and died by suicide in 1954. In fact, actually, Alan Turing is one of, I think, the most important people that lived in the 20th century. He's one of my heroes, you might say, cards on the table. But let's begin here. And the reason why is because As a mathematician, Alan Turing was very, very influential with the birth of modern computer science. It used to be the case that a computer was not a machine. A computer was a human being. A computer was a person. Many, many, many people sitting at a table or a desk in warehouses that were doing computations, doing mathematical calculations. This was a very important job during World War II because they were trying to break the German Enigma code. Right, so these human beings were called computers because their job was to do computations, to do math, and it was important for them to try to, do as much math as they possibly could, as fast as they could, in order to break the Enigma code. But nonetheless, they struggled, as any human being might. Well, Alan Turing had this idea. If we could build a machine that could do these computations better and faster than any human being could do it, then we might have a chance to break the Enigma code. And if you're not sure what the Enigma code was, basically a little background, during World War II, prior to the United States joining the Allies, what happened was the German Nazis were using their, I believe they were U-boats, they were submarines, to create a blockade, right? So basically, the United States were sending reinforcements, sending food, ammunition, and so forth to the UK by boat, and the German Nazi U-boats were sinking them. And so, in order to win the war, we needed to figure out a way to stop them from doing that. But we couldn't because they were using what they I guess was called the Enigma code, which reset itself every single day. There's a really great movie that came out a few years ago. I think it's called The Imitation Game. That kind of is a story about this and about Alan Turing. Watch that if you want to, have a Hollywoodized version of the story, or you can just look it up yourself. But it's a really fascinating, really great story. So basically, the Enigma code prevented us from stopping these submarines from sinking our ships that were supplying, ammunition and supplies and so forth to the Allies. And so, in order to prevent the Nazis from doing this, we needed to break the Enigma code. And so, Alan Turing created the very first, what we might today call a computer that did computations better and faster than any human computer could. So, he was able to break the Enigma code during World War II, which then allowed us, at least partly allowed us, to win the war. So this is a one reason why I think Alan Turing is a really important person in the 20th century. He helped defeat the Nazi army in that regard. It's quite unfortunate, however, because Turing was declared an enemy of the state by Great Britain for being gay. It's really unfortunate, but he ended up committing suicide in 1954 as a result of this. But nonetheless, he's a very important person, very influential. Every person has a laptop or a smartphone or all sorts of different kinds of devices that are largely the direct result of Alan Turing's work and imagining the very birth of computer science. Nonetheless, he committed suicide, and I think it wasn't until about 2014 or so that Great Britain finally recognized him for being the person who he was, and he was no longer considered an enemy of the state. So now let's consider in a little more detail this computer that Alan Turing imagined. Alan Turing thought of this as a thought experiment, what we now call the Turing machine. This is a hypothetical machine that could perform various computations. There's a lot of information we could go into, a lot of details here, but the basic idea is that there would be a kind of a tape that has symbols on it, and there would be a head that reads the symbols on the tape, and the symbols tell the machine what to do. It tells it what its function should be. And so you could essentially, using this tape with these different symbols on it, program the machine to do any particular function. And interestingly, this Turing machine can be instantiated in a lot of different ways. Maybe it's made out of something like wood, or maybe it's made out of metal, or maybe it's made out of silicon, or maybe it's made out of toy blocks like Legos. So the Turing machine is a hypothetical thought experiment, but then it can be realized in a lot of different devices. This is what's known as multiple realizability. The idea, the function, as long as it performs its function correctly, that's all that matters. It doesn't matter whether it's on something made out of plastic or made out of metal or silicon, or maybe even the human brain. Right. So this gives rise to what's known as functionalism as a new theory of the mind. Again, I'm not going to go into all the details here, but the basic idea is that the human mind is a kind of functional machine, or or any sort of mental state that performs a various causal functional role. That is the mind, right? So if you want to think about mental states like pain, or mental states like belief or remembering. What we mean by these mental states, one might say, is that it's performing a particular function or causal functional role in the system. And so that just is what the mind is. It's performing that all sorts of various functions. This is also sometimes called computational functionalism. And what we mean here by adding this notion of computation is that the mind is performing a computation, right? The mind is a kind of a computer program where the mental states are like software and the brain is the hardware. And this was still is a very influential, very popular theory of the nature of the mind. Now, not everybody accepts this theory, and we'll say a little bit more about that in a little bit. But nonetheless, in the 20th century, this was probably the most widely accepted approach or theory to what the nature of the mind is. And again, the nature of the mind is basically the same thing as the nature of a computer, where the mind are mental states similar to the software of a computer, and the brain is like the hardware of a computer. The mind can be instantiated in all sorts of different ways, or it can be realized in multiple ways. It doesn't depend upon it being realized by organic material like what we have in our neurons firing. So it doesn't have to be realized or instantiated in a human brain. It could be, hypothetically speaking, it's possible for it to be instantiated in silicon, like what we have with a computer. And this is what we know as substrate independence, right? Substrate meaning the material that is the basis of the mind, the material that the mind is kind of emerges out of. It doesn't matter what that is, as long as it's able to perform the right functions. That's all that matters, right? So substrate, the material basis of the mind, it doesn't matter what that is, as long as the function works. It could be, organic material, or it could be silicon. So it's independent. The mind is independent of any substrate or basis or material substrate. Now, given that this was a very influential view about the nature of the mind, a natural question comes out of this. If the human mind is nothing more than a mere computational machine that's performing a particular function, then maybe a computer could be intelligent in the same regard or similarly to the way humans are intelligent. Maybe a machine could be conscious the same way that a human is conscious. So this raises the question, could machines think? Could a machine or a computer one day have a mind? How would we ever know? How do I tell whether a machine is conscious or has a mind? Well, how do I know anyone is conscious? How do I know that anyone has a mind? I know that I am conscious and that I have a mind because I have a unique, direct access to my own thoughts and my own phenomenally conscious awareness of my environment. But I don't have that for you. My understanding of your mind is indirect, and that's true for all other minds. Anything that's minded, including animals or pets or anything at all, if we think that it has a mind, it must be based upon its behavior. Must be in some sense based upon what it does, how it acts, including the language that it's using. And that's different than how we know that we are minded, right? I understand that I have a mind directly. I have a privileged access to my own thoughts. I don't have that for anything else. So then we might wonder, how can we test to see whether other things have a mind? More specifically, we might wonder, what kind of test could we use or deploy to tell whether or not a computer has a mind? And this gives rise to what's called the Turing test. Essentially, the Turing test is a kind of a game that we play. It involves an interrogator who questions different respondents or players. On the left-hand side here, we have player A. On the right hand, we have player B. And the left-hand side is nothing more than a computer program. On the right-hand side is a human being like you or me. Now, you as the interrogator or the questioner, you are blocked from seeing or telling who is on the other side of this wall, who's in the other room. So you don't know whether or not you're questioning a computer program or whether you're questioning a human being. And so the basic idea then is you ask the different players questions, trying to figure out whether or not you're talking to a human being like you or me, or whether you're talking to a computer. So what kind of questions would you ask it? What kind of questions would you use to try to prompt it to indicate whether it's a computer or a human being? Now, if it turns out that the computer program could trick you into thinking that it is also a human being like you or me, then it passes the test. The way that Turing is thinking about this and devising this kind of game or test is, there's nothing more to having a mind than convincing someone that you have a mind. That's essentially what we do when we interpret other human beings as having minds, or other non-human animals as having minds. We're interpreting them as having a mind, as being minded, based on the behaviors that they display. Right? So if the computer behaves in such a way by answering your questions such that it tricks you into thinking that it has a mind, then it does have a mind. And so it passes the Turing test. Some people have claimed that our contemporary artificial intelligence, large language learning models like ChatGPT 4 or 5 or whatever is going to come out in the future, that it in some sense has already passed the test, has passed this Turing test. Others think no, it's pretty good, but it's not that good. But we might ask, maybe in the near future, maybe 10 years from now, 20, maybe 50 or 100 years from now, if our computers continue to progress at the same rate, if our technology continues to advance in the same way that it is right now, then it's just a matter of time. Another way of putting that is, artificial intelligence of the general form, intelligence like human beings have, like you or I have, it is possible, even if it's not the case that we have that today. It's possible one day, maybe in the very near future. So what kind of argument might be offered then in support of that sort of view? The view that it's possible, even if it's not actually the case now, nonetheless, it's possible that one day we'll have an artificial general intelligence, intelligence like human beings have, like you or me, or maybe even a super intelligent computer program. What kind of argument might we offer? Well, here's one very famous kind of argument for the possibility of a super intelligent AGI. The first premise says substrate independence is a reality. Remember, that's this idea that if what we think the mind is just computations, these causal functional roles that are being performed in some system that's independent from its material basis or its material reality, right? It can be instantiated or manifested or realized in all sorts of different material bases. Well, if it's independent from any of that, then it looks like that mind can be realized in a machine just like it's realized in an organic system like the human brain, right? So if the mind is independent from its material reality, then anything could possibly have a mind, right? So that's the first premise. It's just substrate independence is a reality. It is in fact true that that is the nature of the mind. It can be realized in all sorts of different material bases. Now, the second premise says, look, we've got lots and lots of little incremental steps of technology progressing, and that seems to be true in the past. And it looks like our technology is developing in a rapid, progressive way. So if it continues that way towards AGI, and if it's also true that substate independence is in fact a reality, well, then it's just got to follow that some sort of a super intelligent AGI would be possible in the future, right? There's nothing that would prevent that. No theoretical, principled reason to exclude that possibility. Even if it's unlikely, it's possible. So that's the general kind of an argument that one might offer. So now let's consider some objections. The first objection we might consider is an objection to the first premise, the premise that says that substrate independence is reality. Now, when we think about the way this view of the mind works, computational functionalism, it basically says that the mind is just performing various functions in a system based upon the syntax that is being used in the computations, where syntax is the manipulation of symbols, the grammar in a language, and so on and so forth, right? So it's just performing various computations over these symbols, over the syntax in a language. That's very different from what's called semantics. Semantics is a relationship between the mind and the world. Another way of thinking about semantics is it involves meaning, some kind of understanding or comprehension of the grammar in the language. The language is being used to make sense of or to give an understanding of what is being said, right? That's the semantics, which is very different from the mere manipulation of the symbols and the syntax, the rules of the grammar in the language. Now, based upon this distinction, which I must say, not everybody thinks that this distinction really amounts to much, but if we think that it does, if we do think there's an important difference between the mere syntax, the grammar and rules in a language, and the understanding of the language or the relationship between the mind, the language, and the world, if that's an important and substantive distinction, then you might think that the computer is merely using syntax but does not have semantics, right? The computer is performing some sort of manipulation of the symbols in which it's reading, but it doesn't understand what it's saying or what it's doing. It doesn't have comprehension. It doesn't have semantics. But you and I do have semantics. We do understand what we're saying. There's a famous thought experiment called the Chinese room, offered by a philosopher named John Searle. And this thought experiment has been influential to really make sense of and use this distinction between syntax and semantics to argue against the substrate independence premise. Another way of putting that is this Chinese room thought experiment has been used to try to show that computational functionalism must be wrong, that computers could never have a mind the same way that human beings have a mind. So let's think about what this thought experiment says. Imagine that you're sitting in a room all alone, and in that room, there's a book. Let's call that book the owner's manual for how to use the Chinese language. It gives you the grammar and the rules, the syntax, if you will, for the Chinese language. And you do not understand or know Chinese at all. You're an English speaker. But you're in that room and you have all of the grammar and syntax, all the rules for the Chinese language. Now, there's a little slat that exists in the room, and people are putting pieces of paper, pushing these pieces of paper through this little slat. So in comes a piece of paper through this slat, and it has a bunch of Chinese symbols on it. Now, you don't understand what it says because you can't speak Chinese, but you have the grammar book You have the rules of the syntax. And so you can use that owner's manual to respond to the questions that are being asked on this piece of paper and written in Chinese. And so you use the owner's manual to respond to the different questions and statements in Chinese and push it back through to the people that are outside of the room. Now, outside of the room, they're reading the Chinese, they understand the Chinese, and so they're able to understand what you just said. But you don't. You have the syntax, but you don't have understanding. You don't have meaning. You don't have semantics. The way that Searle puts this is no amount of syntax will ever amount to semantics, right? So you don't have meaning. You don't have understanding. Now, this thought experiment of the Chinese room is supposed to suggest that what's going on in the computer program is really like you sitting in the Chinese room using the owner's manual, the book of grammar to respond to the people outside of the Chinese room who do understand Chinese. Not everybody agrees, but this is supposed to put pressure on the idea that the first premise should be accepted. The basic idea here is you need the human brain. And so substrate independence is not a reality, that we must reject that premise because the human mind, human intelligence is more than merely the syntax that occur given the silicon functions that are being performed in a computer program. Another kind of thought experiment that has been offered is David Chalmers' zombie argument. But in this argument, in this objection, what we do is we try to imagine a world that's just like this world in every single way. We imagine a human being like you or me that is molecule for molecule identical to you or me. So all of the functions that the brain is performing is exactly like what you or I have. But there's one important difference. The zombie doesn't have any qualitative feeling. The zombie lacks a phenomenal consciousness, right? So that's why this is a philosophical zombie and not your Hollywood zombie that eats brains. So Chalmers' argument basically goes from the idea, it goes from this premise that says we can imagine these philosophical zombies that are molecule for molecule functionally equivalent to you or me, but lacks any kind of phenomenal feeling or phenomenal what it's like to be you or me. And since we can imagine those sorts of creatures, then it must be the case that these are at least in some sense metaphysically possible. These philosophical zombies that are their functional equivalent to you or me are metaphysically possible. So that first premise can be rejected, which is just another way of saying that we're rejecting computational functionalism. Here with Chalmers' zombie argument, we reject computational functionalism because we can imagine a creature that is functionally equivalent to you or me, but lacks conscious experience. So these are different ways that one might object to the first premise. And even if you think that these objections don't quite work, they at least give us some reason to be skeptical, some reason to push back against the first premise, or think that the first premise has not been sufficiently argued for. Right? It's not quite justified. There's some reason to think that it can be undermined. But what about the second premise? Let's look at that premise. The second premise, remember, it says that small incremental steps of technological progress towards AGI is occurring, right? We're just simply moving in incremental steps towards the reality of one day having this artificial general intelligence. Why might we reject that argument or that premise? Well, one reason to reject it is because there's lots of different technological advancements in the past that hit a wall of progress. So why should we think that AI is going to be any different? Another way of putting this is, why should we think that all of the AI hype that's out there is actually more than mere hype? Why should we think that it's any different than all the other things that were once declared as being, these huge technological advancements that never really panned out to be much? Consider all of the different futuristic predictions of the past, right? Think about the claims that have been made, even like back in 2015, involving self-driving cars or self-driving delivery vehicles, right? I remember hearing Elon Musk tell us it's only a year or two away that we're going to have self-driving cars. And that clearly has not panned out. If anything, people are giving up on this idea. Or think about self-flying commercial airlines. Or think about something like cryptocurrency and NFTs. People thought that this was the future. This was where commerce was going. A lot of money was spent investing in these sorts of technologies. And again, it just hasn't really quite panned out. There's a lot of hype, but the technology hit a wall of progress. Or think about the metaverse and other sorts of virtual realities that were once promised as being right around the corner. And these companies are kind of giving up on this technology nowadays. So if we were to take these failed technological advancements as being kind of evidence for what we should expect with regard to our current AI hype, then you might think that AI hype is no different than all these other predictions that were made in the past. So you might think that the AI hype is different. The AI hype is real. It's telling us that something really important is going to happen. Yet at the same point, you might think, well, in many cases, large language models don't exist either. In the previous lecture, I made this point. You might think it was kind of a shocking point. That AI simply doesn't exist because we're talking about two different things. We're not talking about human intelligence or something similar. Well, you might think that large language models oftentimes don't really exist, or at least they don't exist the way that many companies claim they exist. There's lots of companies out there that are facing an extremely high kind of competitive pressure to use large language models and incorporate these into their business model. Because if they don't, then they're going to get left behind in some regard. So you have a lot of companies who are simply rebranding their company in order to kind of keep up with the AI hype, but without really changing much or using any kind of technological advancements. Indeed, many companies have been making millions, if not billions of dollars off of the stock market simply by changing their name without really doing much else. Indeed, this is a really big issue when you think about the major players in AI technology. Right? You've got companies like Microsoft, OpenAI, of course, Amazon, IBM, Google, Meta. So you've got, there's others, but you've got these major companies that are doing all of the investing. All of the major money is coming in from these companies, and they have an incentive to convince the public that this technology is right around the corner. I've got this little graphic on the right-hand side here where you got Microsoft introducing their AI known as Copilot, but it turns out that it's really no different than the kind of technology that they had before. We've already had this kind of chat bot that answers questions for us, or that is claimed to do a lot of the work for us, but really it's not doing much. And if you want some more information about all of this hype that seems to be out there, you might consider the following articles and YouTube clips. There's quite a bit that you can find, and I don't have the time to go into all of it. But it does seem as though there's a kind of false promise of AI changing our society and business in numerous different ways. And if that's the case, then you might think the second premise, there's something wrong with it, that this technology is not going to continue to develop, even though there's this hype around it. Nonetheless, the hype is there purely for economic purposes. It's purely for a capitalist reason to make as much money as quick as possible. But the technology is not as promising as some people might have you think. All the same, there's another reason why we might push back against that second premise. The development of AI technology faces another serious challenge that involves the unsustainable use of water consumption. Our current use of large language models already faces this problem of excessive water usage. We're simply unable to implement the kind of infrastructure that would be needed in order to maintain the electricity demands, via water usage. In fact, many of our current companies are struggling with this problem. So a future AGI would definitely require much more than our current demands already suggest. And if that's so, well, then it's highly unlikely that the small incremental steps of technological progress would actually turn out to all that would be required. Right? It's very unlikely that these the kind of small incremental steps will really amount to AGI in some future technology. And this objection is essentially just an objection based upon the supply and demands of energy. Now, one solution, which is really a kind of interesting take on the issue, promises to at least partly solve the problem via a new kind of technology, a new way of imagining the technology itself, what's called organoid technology. And this technology uses the different stem cells or other kinds of cells that are grown in a lab. Maybe they're neurons that are grown in a lab, and they're under a very specific kind of controlled conditions that are used to mimic the complexity of, say, the human brain. If we were to develop this kind of technology, then the basic idea is that we could use this technology to replace the different aspects of our current silicon based AI technology. And that maybe would allow us to avoid these sorts of problems involving scarce resources, water, and energy, and so forth. Of course, this technology, you might think it's not very plausible. Whether it's plausible or not, I think it's best to just maintain that it's an open question. For more information on this technology, if you're curious about it, I recommend looking at the following articles. I've given the links here. I don't have the space or time to go into it in much more detail, but you may be quite interested in it. So let's remember what the second premise says. That premise says that small incremental steps of technological progress towards AGI is a reality. But if the evidence suggests that we're living in a kind of AI hype bubble, a bubble that will eventually burst, well, then that second premise is either going to be false or it might just simply be unsupported. We might have reasons to be skeptical of it. And that would suggest that we should reject that argument for the possibility of some super intelligent AGI that's going to one day make an appearance in the future.